Howdy. The purpose of this video is to linear densities, planar densities, and atomic packing factors. Now, why do we want to do this? Oftentimes, when we're comparing different directions, planes, or crystal structures, we want to compare their relative densities to each other. So perhaps I care about the density of atoms in one particular direction compared to in a different direction. So I would use the linear density to compare those two directions. Okay, let's do some examples. For the purpose of today's examples, we're going to use the FCC structure to calculate these linear densities, planar densities, and atomic packing factors. Okay, so a linear density is defined as the number of atoms per unit length. So say I'm interested in a 110 family of directions. One example would be this particular direction. I first need to know how many atoms does this direction pass through. And this is a little tricky because I start in one atom, I pass through a second and get to a third, but I need to take into account how much of each of those atoms I pass through. And I can see, since I'm starting exactly in the middle, I'm only going through half of this atom, all of this atom, and then half of this atom. So in this case, n equals 1/2 times 2 plus 1, or equals 2 atoms. Okay, what is the length of the direction I've shown? Oftentimes, this is just calculated in terms of the radii of the atom. So in this case, that length equals 4r. So the linear density of the 110 direction in the FCC structure is just 2 over 4r, or 1 over 2r. Okay, let's try a different example. Same structure, but let's look at the, let's look at the 100 family of directions. 100. Okay, again, linear density is calculated in terms of a number of atoms per unit length. Okay, this example is not quite so clear because the length I can't tell right off the bat. There's a gap there, and I don't know what the relative length of that gap is. Okay, again, the number of atoms here, I go through 1/2 of an atom there and 1/2 of an atom there. So n equals 2 times 1/2 equals 1 atom. The length is not clear at first. So you'll find that oftentimes when dealing with linear densities, planar densities, and atomic packing factors, it all comes down to drawing the right kind of a triangle to get the length that you want, based on things that you know already. So if I draw a triangle like this, this is going to be a 45, 45, 90 triangle. I'm just bisecting the surface, the front surface, which is a square. And I know this hypotenuse already. That is 4r. That's what I used in the previous line. So if I remember my 45, 45, 90 triangles, each of those legs is going to be given by 4r divided by the square root of 2, or 2 square root of 2r. And that is the length of the line in question. So the linear density in this case is going to be 1 over 2 root 2 r. And you'll see that this is a lower linear density than we calculated for the 110 type of family of directions. And this makes sense because if we look at the 110 direction, all those atoms are sitting so that they're touching. They're as close as they can possibly get. Versus the 100 family, there's a gap between them. So we would expect a lower linear density. And indeed, that's what I see. One thing that's worth noting is that I don't need to use the full line as I drew it, because the linear density is independent of how long that line is. So if I just look at this 110 family again, say I just go from here to here. In this case, n equals 1 atom, and the length equals 2r. So again, I get 1 over 2r, which is the same as what I calculated using the previous method. Okay, let's talk about planar densities. Number of atoms per unit area. So now it's a planar density. I'm talking about a plane. I care about the number of atoms per area that I've drawn. So let's look at the 1, 0, 0 family of planes. One example would be this front face in the cube. Number of atoms. Okay, again, I see 4 atoms on the corner, but really only a quarter of those atoms are within this area. So n equals 1/4 times 4 plus 1 atom that's sitting right there in the middle, and all of that atom is in the plane question. So that is 2 atoms. So what is the area? Again, I know this hypotenuse. This is 4r. I know each of these legs are 2 square root of 2r. I just calculated that. So the area is going to be given, this is a square, so it's a squared, where a is the length of one of the sides. So a is 2 square root of 2r, so the area equals 2 square root of 2r squared equals 8r squared. So the planar density for the 1, 0, 0 plane is going to be given by 1 over 4r squared. Okay, let us try a different plane. Again, planar density, number of atoms per area. Okay, let us look at the 1, 1, 1 family planes. And so that is a plane that cuts diagonally through the body of this square. So I'm going to redraw that out here. Oftentimes, if you're given a three-dimensional structure, it makes sense to redraw the two-dimensional projection on the plane that you're looking at. So I can see that the triangle has half an atom, a full atom, and half an atom on each length. And my drawing is terrible. You'll have to forgive me. But all of these atoms are touching each other. And you can look at an FCC structure yourself to convince yourself of that. So first, how many atoms are on this plane? So I see 3 atoms where half of the atom is within this triangle, the area of interest. 3 times 1/2. And I see 3 atoms where 1/6 of the atom is in the area of interest. So 3 times 1/2 is 3 halves. 3 times 1/6 is another half. So this is 4 halves, or 2 atoms. So 2 atoms in that triangle. Okay, what is the area of the triangle? So again, I know each of these lengths is 4r. It's a 60, 60, 60 triangle. So what I'm going to do is bisect that triangle. So now I have 2 triangles that are 30, 60, 90-degree triangles. And I did this because the area of a triangle equals 1/2 base times height. So if I were to call this the base, base equals 4r, and I now need the height, which would be this distance. So in a 30, 60, 90 triangle, this distance is 2r, this distance is 4r, and this distance here is going to be 2 square root of 3r. So again, so that would be the height. Height equals 2 square root of 3r. So 1/2 times base times the height. 1/2 times base times height is going to be 4 square root of 3 r squared. Okay, I put this in, again, remember number of atoms per area. So I have 2 atoms over 4 square root of 3 r squared equals 1 over 2 square root of 3 r squared. And again, we're finding a higher planar density than we did with the other family of planes. And this is making sense because this 111 family of planes is actually a close packed family of planes. You can tell that by these the triangles, the hexagonal packing in this plane. So this is actually the highest packing density you can get for spheres that all have the same size. Okay, so that is planar density. Finally, we're going to talk about atomic packing factor. So this is a little different. Instead of how many atoms, we're actually going to look at the volume of atoms over the volume of the cell. So my units here are going to be unitless. It's volume over volume. The two should cancel out. Volume of atoms, however, is the volume of a single atom times the number of atoms. So the volume of a single atom, we're assuming these are spheres. So V atom equals 4/3 pi r cubed. The number of atoms in the FCC structure, I have half an atom on the top and bottom, half an atom on the front and back, and half an atom on the left and right. So that's 1/2 times 6, plus I have 1/8 of an atom on each of the 8 corners. 1/8 times 8. So 6/2 plus 8/8 equals 4 atoms. So the volume of atoms is just the volume of a single atom times the number of atoms. Okay, what is the volume of the cell? Well, again, this is 4r. This is 2 square root of 2r. Because this is a cube, I can call that A, the length of one side of the cube. The volume of the whole unit cell is going to be given by A cubed. So that equals 2 square root of 2r cubed. So that's 8 times 2 square root of 2 times r cubed, or 16 square root of 2r cubed. Okay, atomic packing factor, remember, volume of atoms over volume of cell. So now I know everything I need to know. My final expression is 4/3 pi r cubed times the number of atoms, 4 atoms, all over the volume of the cell. 16 square root of 2r cubed. And so now finally I just reduce things. 4, 16 gets reduced. R cubed gets reduced. And so I see pi over 3 square root of 2, and this equals 0.74048. You'll notice a couple things. You'll notice the radii canceled out entirely. That's good. When you're doing atomic packing factors, it should be independent of the radii, because if I use a small sphere or a large sphere, that same fraction of volume is always going to be occupied by the atoms for a given structure. Finally, you'll notice this number, 0.74. So this is what we calculate for FCC, and this is also what you would calculate for HCP, because the two are the two close packed structures. So they have the same atomic packing factor, even though the spheres are arranged in different orientations.